Hey, what's up, guys? This is Dr. Vivek Palipuram, and I'm bringing you the next lecturette in ENGR 250 Probability and Statistics for Engineering and Computer Science. In this lecturette, I'm going to introduce you to principal component analysis, which is an important statistical machine learning technique. It's a statistical technique because it relies on statistics such as moments and central moments to explain the data. Traditionally, principal component analysis has been used to perform dimensionality reduction. For example, let's say that you're working for an engineering firm where you need to find the relationship between a dependent variable and several hundreds of independent variables. Now, if you were to plot a relation, or if you were to devise a relationship between a dependent variable and several hundreds of independent variables, you will come up with a model that's going to be extremely complex or complicated. In addition, analysis of such a data becomes quite unwieldy, and not only that, you'll be performing overfitting with your model. So instead, what engineers or scientists tend to do is they remove or eliminate least important variables and only retain the most important ones. And principal component analysis helps you to perform this analysis. Specifically, principal component analysis gives you a set of principal components which are the most important ones that describe the data. The principal components that are the most important ones are the ones that you are going to retain for explaining the dependent variable in terms of the independent variables. So for example, let's say that I'm a computer engineer and I have a dependent variable which is dependent on these variables. Let's say f is dependent on g, h, I, j, and k. So I have 5 variables here which are the independent variables which influence my dependent variable f. Now, the principal component analysis, what it is going to do is it's going to rank these individual variables, these individual independent variables, based on the magnitude of their importance. And there are some numerical methods to do that in principal component analysis. So let's say that hypothetically, this one is the most important, or it is the most highly ranked variable that explains the data f. Let's say that this is rank 2, then this is 3, and this is 4, and let's further say that this is 5. Now, principal component analysis allows you to choose only specific components to explain this data. So in this case, for example, 4 and 5 are the least ranks. So G and H have ranks 5 and 4 respectively. So they have the least ranks, they have the least importance. So one can eliminate these variables and only explain f in terms of I, j, and k. In this way, whatever model results with whatever analysis that you're performing, for example, regression, for instance, that model is going to be much more simpler versus a model which also considers G and H, in which case there will be 5 variables and the model is going to be quite complicated. So that's where principal component analysis comes to rescue. Principal component analysis is used to perform dimensionality reduction to only find out those variables which really affect the dependent variable so that we can perform some sort of a model fitting. In fact, principal component analysis has been widely used in image processing to explain the shapes of different objects and to perform object recognition. It's a very simple technique that relies on statistics of individual objects, and then using those statistics, it tends to identify how the data is distributed, whether the object is elongated or it is circular or it is an irregular shaped or what have you. Such analysis helps a lot to perform computer vision. And in fact, one really nice application would be to enable a robotic arm to pick an object from an image. For example, if I were to pick this particular object, let's say that I want to pick this banana, I need to find its dimensions. So what I can do here is use principal component analysis to find where the center of this object is located, using the statistics that principal component analysis uses, and also draw axes that show the orientation of this particular object. So for example, it tells me that this object, principal component analysis is going to tell me that this object is oriented in this way, where this long line is the major axis and this short one is the minor axis. So a robotic arm can adjust its grasp accordingly, and using the center of this object, it can place the robotic arm in a proper place and then just pick it up. So that's a real life application of principal component analysis. As I mentioned, this analysis uses simple statistical parameters like moments and central moments, which are performed or which are calculated very easily to perform such neat tasks. For your midterm number 2, exam number 2, where you need to program for principal component analysis with a partner, here's what you need to do. I'm going to give you a boilerplate code that already performs some sort of image processing. Specifically, it takes in an input image and then it separates all of these individual objects inside of this image and labels them with separate component. For example, this particular banana right here will be labeled, all the pixels in this banana will be labeled with a unique label, indicating that any pixel corresponding to that label belongs to this banana. So each of these objects, you have tangerine, you have apple here, and you have another apple here. There's a banana hidden here as well. So all those different objects are going to get different labels. What you need to do is you need to visit these individual labels and extract their statistics with respect to how their pixels are placed in the X and Y dimensions. And using those statistics, you need to find out whether these objects are elongated or they're compacted or they're circular in nature, how many pixels contribute to these individual objects, and so on and so forth, their sizes, etc. And then use those statistics to perform object recognition. Specifically, what you'll be doing is you'll be using principal component analysis to identify their centroid or center of mass. Not only that, you'll be placing these cross signs on them, and which are composed of two axes which are perpendicular to each other. One of them is going to be a longer axis, which shows where exactly or how the object is oriented in the space, and then perpendicular to it will be the minor axis. So this shape right here, it tells me that that's the orientation of that banana. This shape here tells me the orientation of this banana, and these crosses on the tangerines show me the orientations of these individual tangerines. So that's what your goal will be. Your goal will be to identify the centroid of these individual objects and then place appropriate major and minor axis on them using principal component analysis. So what follows next, I'm going to show you how principal component analysis uses very simple stuff like moments and central moments to perform such neat activity. So let's talk about moments here. In phase 2, you were introduced to moments and central moments for two-dimensional random variables x and y. So expected value of xy gives you the p is equal to 1, q is equal to 1 moment of x and y. So we'll be performing a lot of moment calculations with our respective image, with our labels image that has objects labeled in it. And then we are going to perform the principal component analysis. So we are going to be using this label image called f, and we are going to compute the moments and central moments of all of these individual objects which have a specific label value L. So for each labeled region, we are going to obtain the statistics. There's one interesting aspect that each of these objects are labeled differently. So for example, an object, let's say this banana, for hypothetical reason, let's say that it gets a label equal to 80, then the other objects, including the background, are going to get other labels except for 80. So a region or this image can be considered as a binary with respect to a particular region. So for example, a label or rather an object will be having a label equal to 80, or it's not going to have a label 80. So this helps us to perform an important assumption that f of xy can be considered equal to 1 if both x and y belong to a region of a particular label. This is going to be our assumption just to simplify our calculations with respect to moments and central moments. Now, the calculation of moments and central moments is pretty mechanical in nature. So in what follows, I'm going to show you how to calculate the moments and central moments. So it may be a little bit boring, but using those statistics is what makes things much more interesting. So as I mentioned before, the pqth moment of a 2D region with label L can be calculated in this particular manner. So the pqth moment is given by summation for all the x that belong to the region L, summation y that belong to the region with label L, x to the p times y to the q times f of xy. And in our assumption, f of xy is considered as 1 for a particular label that we are considering. So simply the pqth moment boils down to summation X belongs to a particular region L, Y belongs to a region L, X to the P times Y to the Q. X and Y here are correspondingly the X component and the Y component of a particular location. So what I'm going to do is I'm going to gather all the pixels corresponding to a particular region, get their X values, get their Y values, and apply this particular formula to calculate the pqth moment. In order to find the center of mass of a particular object, I can find the centroid using this equation here. So M10 can be obtained by placing P as 1 and Q as 0. So it will be just summation, double summation of all X. And similarly, M01 will be double summation of all Y divided by M00, where M00 essentially means how many pixels are there of that particular attribute L or that particular label L. So this gives me the center of mass. So it's going to give me the average, this particular factor is going to give me the average X for the X component of a particular coordinate, and this is going to give me the average Y component. So both XC and YC together, they give me the centroid of a 2D region with a particular label L. So that's how you find the centers of these individual objects. So these centers here are XC and YC, which are found using this formula, M10 over M00, comma M01 over M00, where M10 can be calculated by plugging in or using this equation and substituting P as 1 and Q as 0 and vice versa. So that's very, very mechanical calculation with respect to calculation of the centroid. Principal component analysis also depends on the central moments, and central moments are obtained in this manner right here. So to find out the pqth central moment, you apply this double summation formula. The reason why you perform this double summation is because your images are 2D that you're trying to analyze. So that's going to be double summation x minus xc to the p times y minus yc to the q times fxy. Now, because we have assumed that fxy is equal to 1 if we are particularly focusing on a particular label, so this boils down to this simple equation right here. Mu pq is double summation, that entire thing. Other attributes like variance of x, variance of y, the covariance of x and y, they are pretty mechanical with respect to calculations, and it is not difficult to prove that the covariance of x and y is given by this formula. The variance of variance of x is given by this formula, and the variance of y is given by this formula right here. And all of these formulas you have already applied when you were solving for different problems in your quote-unquote homework or your turn problems. You have performed this calculation. Now it's time for us to have computers solve these explicit calculations for us. Mu00 here, in this case, just simply represents that how many pixels are there for a particular object with label L. Mu11 gives you the covariance of x and y. It gives you an indication how x is varying with respect to y. It tells you, based upon its sign, whether if x is increasing, is y also increasing, or if x is increasing, is y decreasing, and vice versa. Mu20 gives you the variance of x, so it tells you how much data is spread about the x-axis, and Mu02 gives you the variance in terms of y, variance in the y direction. Now let's solve one problem with respect to the computation of moments and central moments. Because these formulas are quite mechanical in nature, we will be performing this in MATLAB, but it's always a good idea to perform these calculations by hand so that you're able to set up for loops to perform those operations easily. So here, what I need to do is I need to calculate the moments and central moments. Well, specifically, I need to calculate these parameters, mu11, mu20, mu02, and mu00 for a region that has label equal to 4. So if you notice here, this is the region with label equal to 4. So I need to perform the calculations of mu11, mu20, mu02, and mu00. So first, let's start with the calculation of its centroid, where exactly the center is. Now, MATLAB is going to view this particular matrix starting from 1, 1 all the way to 5, 5. Which means that this location is going to have the coordinates as 2, 4, this is 2, 5, this is 3, 3, 3, 4, 3, 5, and this one is 4, 3, and this one is 4, 4. Now, XC is calculated as m10 over m00, and yc is calculated as m01 over m00. So that's the centroid, xc and yc. So to calculate m10, I need to perform summation for all the values of x in the region that have label equal to 4, summation y for all the region that have label equal to 4. I need to perform x to the 1 times y to the 0. So these are the location where the label is equal to 4. So what I'm going to do is to calculate m10, I'm going to add the x values for all these locations. So I have 2 plus 2 plus 3 plus 3 plus 3 plus 4 plus 4 for these two guys. So that gives me the value of m0 as, let's say, 2 plus 2 is 4, plus 3 is 7, plus 3 is 10, plus 3 is 13, plus 4 is 17, 21. So m10 is 21. M00 is just summation for all the x in this region, summation for all the y in this region, x to the 0, y to the 0. Essentially, I am just adding 1 to itself over this entire region. So I have 1, 2, 3, 4, 5, 6, 7. So if I were to add 1 7 times, I'll get m00 as 7. And similarly, m01 is summation x in this region, summation y in this region, x to the 0, y to the 1. So I'm going to add the y component of all this location that have label equal to 4. So I have 4 plus 5, that is 9, plus 3, that is 12, plus 4, that is 16, plus 5, that is 21, plus 3, that is 24, plus 5, plus 4, that gives me 28. So m01 is 28. So the center of this object, xc, yc, is 21 over 7, 28 over 7, which is 3 over 3, 4. So this guy right here is the centroid, and you can see that this indeed is the center. I hope my calculations were not off. Even if they were off a little, your centroid will be somewhere around here, which is at location 3, 4. So that gives you the centroid. Similarly, once we have computed xc and yc, we can compute mu10, mu11, mu20, mu02, and mu00. Well, mu00 is actually equal to 7. Let's focus on mu11, the covariance of x and y. How is x varying with respect to y? If we were to assume that this axis is x and this axis is y, and these are the increasing directions of x and y respectively, we will be interested in finding out whether x is increasing with respect to y or decreasing, meaning that if x increases, does y increase, and vice versa. So let's find out. So mu11 is found by applying this formula, m11 minus yc times m10, or m10. So mu11 is m11 minus yc times m10. I have calculated m10 already, which is equal to 21. To calculate m11, I need to perform double summation. X belongs to this region, y belongs to this region, xy. So I need to multiply xy of these coordinates and add them all together. So here I have 8 plus 10 plus 9 plus 12 plus 15. Then here I have plus 12 again, and I have plus 16 here. So 8 plus 10 gives me 18, plus 9 gives me 27, plus 12 gives me 39, plus 15 gives me 54, plus 12 gives me 66, plus 16 gives me 82. So m11 has evaluated to 82. So mu11 is 82 minus yc, which is 4, times m10, which is 21. So that gives me 82 minus 84, which is equal to negative 2. Which is equal to negative 2. So as x increases, y seems to decrease. So, and you can observe here that as x increases, y seems to be decreasing here, like that. So covariance is negative. It shows that as x increases, y decreases. So that's how these moments and central moments give you an indication of how this object is shaped. Similarly, I can calculate mu20, which is going to tell me how much variance is there in the x direction, and mu02 is going to give me how much variance is there in the y direction. Depending on their magnitude, I can guesstimate what the size or how this object is shaped. For example, if both mu20 and mu02 are equal to each other, then that means that the shape is quite circular because I have equal variance in both the x direction as well as in the y direction. If I have greater variance in the x direction but smaller variance in the y direction here, so in that case the variance of x is going to be large and the variance in y is going to be small. So by looking at the variance of x and y, I can guesstimate how the shape of this object is going to be like. So statistics, the statistical parameters, the moments and central moments give you a lot of indication as to how the data is spread. And principal component analysis helps us to bring those dry values to life. So long story short now, so far we have discussed how to perform calculations of moments and central moments, and we have been talking about the fact that these moments and central moments help us to find out the shapes of the objects. Principal component analysis is the analysis technique which brings those dry values to life. Specific goal of principal component analysis is to plot an ellipsoid about the data and mark the major axis and the minor axis. The major axis tells you in which direction the data is spread the maximum, and the minor axis is the next important direction. So when you have several variables, you may have several major and minor axes. The longest ones of these axes will be the most important one. So for example, let's say that I have 4 variables, and if I were to draw these, or rather 5 variables, and if I were to have these 5 components or 5 principal components, out of them the longest ones will be the most interesting ones. So I can use these 2 longer components to explain the data. For our practical purposes, our job is simple because most of the 2D images, our images will be considered as 2D, so it will have only the x component as well as the y component. We have already seen how to compute the center of these objects, xc and yc. That's a very simple computation. All you need to do in MATLAB is for each label, you need to perform your double summation. So for all x in region L and for all y in region L, you need to compute those computations that I had showed you before. So calculation of xc is rather easy. Now the orientation of the axis, how these 2 axes are oriented, and the length of these axes are given by the principal component analysis, which uses an algebra technique, a linear algebra technique, wherein it performs the following. So it first obtains a covariance matrix. It obtains a covariance matrix where mu20 here is the variance of x, mu02 is the variance of y, mu11 are the covariance of x and y, and it's a straightforward fact that mu11 is going to be equal to mu11. So this entire thing is your covariance matrix. Now what the principal component analysis does is obtains the eigenvalues and eigenvectors for this particular matrix C. And eigenvalues and eigenvectors are obtained as the determinant of C minus lambda I is equal to 0 by solving this equation, where I is your identity matrix 1, 0 and 0, 1. Some of you may have taken linear algebra, some of you may not have taken the linear algebra, so it's not wise for me to go into the linear algebra aspect of principal component analysis, but rather give you a more, or rather explain you PCA in a more qualitative fashion. So if I were to solve this equation for this 2D matrix C, I'm going to get 2 values of lambda because I have C, which is a 2-dimensional matrix. Lambda 1 and lambda 2 are my principal components. These are the principal components. The lambda value, which is the largest, is going to be the major component. So let's say that lambda 1 is greater than lambda 2. So this is going to be a major component, which is going to tell me in which direction the data is spread, or which is the majority direction where the data is spread. And lambda 2 is the next important component, which is not as important as lambda 1. Along with these eigenvalues, you also get something called as the eigenvectors. So corresponding to lambda 1, there's going to be an eigenvector v1, and corresponding to lambda 2, there's going to be eigenvector v2. And as the name vector suggests, it gives us the directionality. Both of these eigenvectors are going to give the directionality of the data as to how it is spread. Civil engineers may have much deeper understanding of vectors because they work with forces on objects all the time, and they can attest the fact that vectors give you the direction in which the force is being applied. Similarly, eigenvectors of lambda 1 and lambda 2 are going to tell me in which direction my object is oriented. So principal component analysis is going to use this vectors and eigenvalues to give me the length of these axes as well as the direction of these axes. So let me give you the actual formula to obtain the eigenvalues and eigenvectors, or specifically the length of these principal axes as well as the direction of these axes. So because our covariance matrix is two-dimensional in nature, I'm going to have two eigenvalues which can be computed by applying this particular formula, where mu20 and mu02 are, and mu11 are the values inside of my covariance matrix. So this is going to give me two eigenvalues. One eigenvalue can be obtained by applying mu20 plus mu02 plus this discriminant form. The smaller eigenvalue can be obtained by applying this -1. So lambda 1 is going to be the one which uses the plus sign, and lambda 2 is going to be the one which uses the minus sign. So naturally, lambda 1 is going to be greater than lambda 2. The length of the major axis, the half length of the major axis, is given by this form right here, 2 times root of lambda 1, and the length of the semi-minor axis is obtained by 2 times root of lambda 2. And the direction, how the data is spread, is obtained by using this formula. Theta is equal to 0.5 times a tan 2, where a tan 2 is a MATLAB function, 2 times mu11, comma mu20, comma mu02. So linear algebra has given us all of this formula, and we are not going to go into the derivation of those aspects because not everyone may be familiar with linear algebra in our class. So once you have obtained the major axis and the minor axis, you can actually use MATLAB to perform the drawing of these axes. You would have already identified the center of an object, xc comma yc. So as I mentioned before, 2 times root of lambda 2 is going to be the length of the minor axis, and 2 times root of lambda 1 is going to be the length of the major axis. So, and these two are going to be perpendicular to each other. Using some trigonometry, you can perform drawing of these lines in MATLAB. So what I would like for you guys to do is work with your partners, Google search how to draw lines in MATLAB. So most likely it's going to give you a function that takes in two coordinates, x1, y1 and x2, y2, and it just simply joins those two lines. You have already obtained xc and yc. It's easy to show that this point right here, which is at an angle theta and at a length let's say 2 times root of lambda 1, will be at this location, cos theta times 2 times cos theta times root of lambda 1, and its y location will be yc plus sin theta times 2 times root of lambda 1. And similarly, you can obtain this point by applying simple trigonometric concepts. This application of trigonometry is not that difficult, but should you need help in this regard, you can always get in touch with me. So once these points are drawn, you can just simply use MATLAB to join those two lines using an appropriate axis. So this drawing axis will help you perform this particular aspect. Just simply draw the axis about these objects. So these axes will be drawn using the length of the principal axes, the major and the minor axes, and by finding the center of these individual objects, xc and yc. That's going to be, I would say that's a straightforward process. But now the most important part is the analysis, where you not only have to draw the axis on these objects, but you also need to change the color of these objects corresponding to the objects that they are representing. For example, oranges or tangerines in this case are labeled with orange axes. The apples are labeled with red axes, and banana are labeled with the yellow axes. using these statistics like moments and central moments and the length of the major axis and the length of the minor axis, what you need to do is you need to inspect each of these individual objects. What you need to do is, if I were to consider this banana, how are its statistics? What you need to do is find out the magnitude of the statistics of each of these individual objects. For example, if I'm looking at bananas, I'm going to look into their statistical values, and find out how they look. Based on their statistics values, I'm going to identify whether an object is apple or banana or what have you. So for example, if you were to consider a banana, for instance, it's going to have a lot of variance in one direction. Let's say, well, in fact, this has a lot of variance in this direction. There's a lot of variance, but a very small variance in this direction. So that gives you an indication that it's an elongated object, which may look like a banana. A tangerine is quite circular in shape, so it may have equal variances in both x and y directions. So by inspecting statistics like this, you will be training your machine to recognize objects in other images. So what you'll be doing is you'll be analyzing fruit1.bmp and study the statistics of these individual objects, and then hard code these statistics to train your computer detect the objects in another image, fruit2.bmp. So that's what you guys will be doing. Using statistical knowledge obtained from fruit1.bmp, you'll have your computer detect objects inside of fruit2.bmp, and objects inside fruit2.bmp is going to be either apples or bananas or tangerines. There are some other additional statistics that you can use to identify whether an object is circular or whether it is elongated, and that statistic is eccentricity. Eccentricity is defined as square root of lambda max minus lambda min over lambda max, where naturally lambda max is equal to lambda 1, the larger of the two eigenvalues, and lambda min is going to be equal to lambda 2. So if both lambda 1 and lambda 2 are equal to each other, meaning that the shape is circular, you'll identify that the eccentricity value is going to be equal to 0. If the object is quite elongated, then this eccentricity value is going to be larger. So right now I'm giving you some hints as to how to perform the statistical machine learning. Rest, I would leave it up to you. I understand that you may have some issues with programming, so I will help you guys with respect to programming, but with respect to actual statistical analysis, you guys are on your own. You need to discuss on your own. I think it's a really good time to stop this lecture right here. This lecture introduces you to principal component analysis and tells you what you need to do in your midterm 2 or exam 2 programming part.